So last time we were at there were three row operations, and all three of them can be represented by elementary matrices. To like after conduct matrix multiplication, we will get the same thing as the row operations. So for row exchange, we just exchange the places of ones for I and j. And for scaling, if we want to scale row I, then we change the identity matrix at I to be alpha. And for row replacement, if we want to replace Rj with Rj plus alpha Ri, then we just find the place where it's the jth row and ith column and make it alpha instead of 0. So these are three elementary matrices. And after that, we will be able to find the inverse matrix with the multiplication of elementary matrices. So this is the first way of finding the inverse of A. There is another way. After we introduce the determinant, it will be easier. But the idea to find the inverse, say 2.4 inverse of A. So we say any invertible matrix can be row reduced to the identity because we've said that the invertible matrix or the isomorphic transformation basically has one pivot in every row and every column. So we know that any invertible matrix So then if we want to find the inverse of A and we name it as X, we basically want to find a multiplied by the matrix X, where this product is the identity matrix. That's the definition of the inverse. And we know the I is basically a collection of columns where each column is the standard basis. EI. So if we say X is a matrix where each column is named Xi, then we're looking for a multiplied by x1, x2, all the way to xn. That gives us the EI. Hello.
Hi.
Are we using your place?
Sorry?
Are we using your place?
No, it's fine.
Okay.
Yeah.
E1, E2, all the way to En.
The new summer student.
Yes.
Okay.
Hello.
Okay, then what we're doing is actually to find xi's. That gives us a times x1 equals e1 all the way to a times xn equals en.
But I thought A in itself is a matrix. No?
Yes.
Oh, so this is row A, row A1.
No, this is the matrix A. Yeah, so this is like a matrix multiplied by vector equals another vector.
I'm looking for how matrices.
That's like ax equals b.
I kind of forgot that part.
Oh.
I'll look at it. It's fine. Oh yeah. Okay.
Great. So then what we can do is basically to
Because I thought when you're solving for the kernel, you set a times x to 0, right?
Right.
And so this is when you're trying to find the inverse. You
Yes.
set it to I.
Right.
Oh, okay.
Yeah. So so basically what we're doing, we can also use the language of row reduction to find the matrix. So the steps to find the inverse of A is basically first row reduce matrix, the augmented matrix, and on the left is the matrix A, on the right is the identity matrix. And second, if after the row reduction we get the row reduced echelon form to I on the left and x on the right, then we say A is invertible and x is the inverse. If we see results otherwise, then A is not invertible. So then we have a definition. We say the dimension of a vector space V is the number of vectors in the basis for V. However, very special, if my vector space is just the zero vector, then we say the dimension is 0.
So like, what would R squared, like if R squared is the vector space, the dimensions of R squared?
What do you think? How many bases, like how many vectors in one basis for R squared?
Isn't it like just all real?
Just what?
Isn't it like, oh, 2? Okay.
So a typical basis is 1, 0, and 0, 1. So there are 2 vectors in the basis. We say the dimension is 2. Let's skip things. All right, then let's introduce rank. So the rank of matrix is actually just the dimension of the range, if I remember correctly. Okay. We've introduced how to find the basis of the kernel and basis of the range. So basis of kernel was to solve AX equals 0 and then find the kernel vectors. And basis of range is to find the pivot columns and then find the original columns. I can find it. It's right here. So basis of kernel, we find the kernel vectors after we solve AX equals 0. And basis of range is to find the pivot columns are these green ones, and then we find the original columns, and these 2 columns will be our basis for the kernel, for the range or the image of A. Okay, so after we have that,
So does something with a unique, like a matrix with a unique solution, so there isn't like, it doesn't depend, it's not relative to a variable, does it just not have a kernel?
Then the kernel is just the 0 vector.
Oh, okay.
Yeah. And the dimension will be 0 for the kernel.
So the 0 vector doesn't count as a vector?
Yeah, in a sense.
Okay, I see.
Okay, so we define the rank. Rank of matrix A equals the dimension of the range of A, or similarly the dimension of the image of A. And there is a special theorem saying that for any matrix A, the range of A, the rank of A equals the rank of the transpose of A. Okay, and another theorem called the rank nullity theorem. We say if we have a matrix n by n, first the dimension of the kernel of A, because kernel is called the null space, so that's the nullity in the name. So dimension of the kernel of A plus the dimension of the range of A. And again, dimension of range of A is just the rank of A. Equals the number of columns. Second, the dimension of kernel of A transpose plus the rank of A transpose equals the number of rows. So last time we introduced the basis of kernel A equals the free columns when we solve AX equals 0. So that's the orange columns. This, and this. And the number of bases in the range of A is the pivot columns. So these two type of columns constructed to all columns, and that's why if we count the dimension of kernel and dimension of the image, we get to the number of columns.
Okay.
Yes. And and in this case, our rank equals 2. So this means rank of A equals 2. Dimension of the kernel equals 3. We introduce another definition, we can go to determinants. So we didn't do any practices for finding the inverse of A here, because we are going to introduce a easier way to do that. So one definition, we call a matrix is similar, we say matrix A is similar to B if there exists a invertible matrix Q and invertible such that A can be written as Q inverse times B times Q. So note that we already know that invertible matrices are square matrices. So Q is invertible means the...
Wait, isn't this just I?
Yes, but matrix multiplication cannot be, it's not commutative.
Oh, yeah.
Right.
Okay.
But you can write this as, if you multiply by a Q on the left side, then you can write this as QA equals BQ. So since we know Q and Q inverse is invertible, then we say this, we know that Q is a square matrix, and we just call it n by n for some arbitrary n. Okay, now if Q and Q inverse is n by n, then that means A and B are also n by n. Because Q need to multiply by B, so B has to have
and the other side is n.
right n rows, and the other side is also n, so B needs to have n columns, and then the result is n by n, so A is also n by n. So from here we know that for two matrices to be similar, they have to be square matrices and have the same dimension. Okay. Right, now introduce determinant. Chapter 3. So determinant is important in matrix. So we use it to find the inverse of matrices, and determinant can also tell us like some properties, such as if the matrix is invertible or not. So let's look at how do we define determinant. So for a determinant of a matrix, it is defined on square matrices. So the determinant of a matrix A n by n is a scalar. It will just be one number to represent a matrix. So we say that for matrix A, the determinant, we use this notation DETA, is the volume of the parallel piped
Wait, what is that word?
Yes, parallel piped.
Oh, okay.
Yeah. Determined by the column of A. So that means, for example, if we are in the R squared space, and we have the matrix A equals 1, 2, 0, 4. Okay, then the volume in this case equals the area. So I will have the x and y axis, and the first column is 1, 2. So we'll draw that vector. It's right here. And then the second vector is 0, 4. So it's over here. All right, and the determinant is the volume, and in the 2D case, volume is the area. Okay. Now we calculate the volume. It will be the base times height. In this case, the height is 1, the base is 4. So the determinant equals 4.
So because r squared volume is area.
Yes.
Doesn't this get really nasty when you're in like more than r cubed?
Exactly. We're going to find a better way to calculate in that case. Okay. And when we're in the r cubed case, so if a is 2, 1, 0, 1, 3, 0, 0, 0, 2. We have x, y, and z. Okay, now the first factor is 2 in x direction and 1 in the y direction. So let's see here. Alright, second one is 1 in the x direction, 3 in the y direction. So let's see here. And third one is 2 in the z direction. Okay. Now the volume in this case is
Did it like
and if we write A as the columns vectors, v1, v2 through vn, and that's a matrix look like A1, 1, A1, and okay, then we write determinant of A. We can also write determinant of the vectors v1 through vn. And we can write it as the, if we are using a matrix, then the determinant will be represented by 2 straight lines or segments, and the matrix is in the middle.
So you said you use the determinant to find out if a matrix is invertible or not?
Yes. So we're going to explore some properties, and that will be our result from the properties, the linearity in each argument. So that means that if we have if we're in R squared, and we have v1 and v2 like this. And if we want to multiply v2 to 2v2, then the volume or the determinant will also double. So that means determinant of v1, v2, v1 to v2 equals the twice of the determinant of v1, v2.
So does linearity just mean that it increases? It changes like proportional to, but the proportion isn't necessarily 1-to-1 all the time. Like
In this case,
really
it is.
Shape, but can you ever get a really weird shape? Like if you have a trapezoid, like changing one thing is not gonna proportionally change. It's by a 1-to-1 proportion.
It will, because when we double one vector, then it means, so in this case, this vector could be like v could be 1, 0, and 2v could be 2, 0. But if you're in the other, like if we're using the other shape, maybe v2 could be like 3, 1 at first, and then 2v would be 6, 2. So in either case, like the length is doubled, and if we treat it as the base and we multiply by the height didn't change, so the volume would be doubled. Have row replacement. So we're actually looking at the row operations that we can do to a matrix. Alright, in this diagram again, still we have v2 and v1 like this. And if I want to replace v1 to v1 plus 2v2, so determinant of v1 plus 2v2 and v2. So in the graph, I will have v1 plus 2v2 will look like this. That's vector addition. And then we have v2 here. So our parallelogram will look like this. Right. But in this case, we still have the same length of the base and we have the same height. So this actually equal to our original determinant or original volume. So antisymmetry basically means our volume is, we have assigned volume. So if we have v1, v2 like this, and we say the volume is base times height like this, then we say the determinant of v2, v1 is actually the negative of determinant v1, v2. So we define volume with sign. So that means if we have a matrix where we have two columns switched, so V1, V2, and there are some Vi, and after something there is a Vj all the way to Vn. Then if we switch these two, we say the determinant will be switched sign. V1, 2, this place is Vj before Vi.
So like switching, when you switch the vectors, so you're just switching the columns, right?
Yes.
How does that? It shouldn't change the area or the volume.
Right. It doesn't when we talk about volume like normally, but we define a sign to the volume. So then in our definition, if we switch two rows, if we switch the two vectors, then we change the sign. It's a new definition.
Oh, okay.
Yeah, to the volume. Right, the last one is called normalization. Okay, so that means if we are using standard basis, for example, in R2, if we say that if we want to find the determinant of E1, E2, in R2, basically 1, 0 is E1, 0, 1 is E2, and this column is just this volume is just 1. But also, if we're in the R3, if we have another dimension and this is E3, then we will have a cube, but the volume of this cube is also 1.
Yeah.
So basically, when we're dealing with a determinant of the identity matrix, because E1 is 1, 0, E2 is 0, 1. So this is, in this case, this is the identity matrix in R square. And here also, like E1 is 1, 0, 0, E2 is 0, 1, 0, E3 is 0, 0, 1. So this one would give us, basically, determinant of an identity matrix is just 1. So we have 4 properties, but actually the second one can be represented by the other 3 properties. So let's look at some propositions. So the first one is if we have a matrix with a column that's all zeros, then the determinant is 0. So this is like if we're calculating volume and one of the dimension is 0, and 0 times everything is 0. Okay. Now another one, if A has 2 equal columns, then the determinant is also 0.
It just doesn't work.
It works because but it is 0 because if we do row replacement, we can change one row. So if v1 is 0, if v1 is equals v2, then we can say we want to replace this row with v1 subtract v2, and then we will have a column with all zeros. So very similar. If we, instead of using v1 subtract v2, we're using v1 subtract like 2v2, then we get to our third proposition, where it says if one column is a multiple of the other, then also the determinant will be 0. And the fourth, so if we not only like change this row to v1 plus or subtract 2v2, but also if there are 3 vectors, we have v1, v2, v3, and I know that v3 equals 2v1 plus v2, then we can basically say we first replace v2 to 2v1 plus v2, and then we use v3 to subtract the second column, the new second column. Then we will also have a column of zeros, and in this case our determinant will also be 0. So the fourth is saying A has columns that are linearly dependent. Then the determinant is 0. And this is actually like if A has columns are linearly dependent, then this is actually equivalent to A is not invertible. And then we know that if A is not invertible, then the determinant is 0. Okay. Now let's define So we call a matrix is diagonal. A square matrix is called diagonal if all entries in the main diagonals um, or of the main diagonals. Is 0. So basically, when you have a identity matrix, you know the diagonal looks like all ones, but all other entries are 0. So this is like the identity matrix is diagonal. But there are other matrices looks like.
Wait, it's called diagonal if all entries of the main diagonal are 0.
Off, like outside.
Oh.
2 Fs. So the diagonal matrix will look like A11, A22, A33, all the way to ANN. But other entries are 0. And then we can see how do we calculate the determinant. So we know that the determinant, okay, so let's say this is A. So we know that the determinant of I is 1. And we know that I is E1, E2, E3. So now we have the determinant of, let's say the first column is A1, the second column is A2, and all the way to AN. So basically the determinant of A in this case is determinant of A1, A2, all the way to AN. And now A1 is this A11 multiplied by E1. A2 is this A22 multiplied by E2, all the way to ANN multiplied by EN. Okay, and we know that if we're multiplying something to one vector, then this is our linearity, the first property. So we can actually extract this A11 out, and that would be equal to A11 times the determinant of E1, and then A22, E2, and so on. And we can basically extract each factor outside. So then we will end up with A11 multiplied by A22 multiplied by all the way to ANN to multiply by determinant of 1, I, identity. And we know the determinant of identity is just 1. So the determinant of this a diagonal matrix is just the product of all diagonal entries. A11 multiplied by A22 all the way to ANN. Product of diagonal. Okay, now let's also introduce some triangular matrix.
Triangular matrix?
Yes. So right now we have diagonal matrix, and then we define triangular matrix to be, so we have two different triangular matrix. There is one called upper triangular matrix. So a matrix A is upper triangle. If all entries below the main diagonal
So not including.
right is 0 are zeros. Okay, so it'll be a matrix looks like so there are some entries A11, A12, A22 all the way to ANN, but here are all zeros.
Wait, so the main diagonal, I thought you said the main diagonal is also 0.
Below the main diagonal
Okay, so
does not include. So this is a triangle, like the upper triangle is filled with entries, but the bottom is just 0. Okay, similar for lower triangular. So A is lower triangular if all entries above the main diagonals are zeros. Okay, and we say the determinant of the triangular matrix. So we can tell right now that if we just want to, so if A11 is a number, let's say 2, and A12 is a number, let's say 3. Thanks. And then we can basically say, we can basically replace the column A2 to be A2 to be 2A2 subtract 3A1. And in this case, we can eliminate this entry. So basically, a triangular matrix, we can do column operations so that we can reduce these to a diagonal matrix. So then we know that for a diagonal matrix, we can find the determinant to be just the multiplication, the product of all diagonal entries. So similar for this one. So we say the determinant of a triangular matrix either is upper or lower. Also equals the product of diagonal entries. Okay. Okay, now let's look at the theorem. So this theorem, we already talked about it, is that determinant of A equals 0 if and only if A is not invertible.
Yeah.
Okay. So we already talked about the backward, where if A is not invertible, then A is like has great linear dependence, so then the determinant has to be 0. So the forward direction, if the determinant equals 0, then A is not invertible. We can prove by contradiction. So suppose A is invertible. So if A is invertible, then we know A transpose is also invertible. Okay, if A transpose is invertible, then that means we can do row reduction. So we can do row operations to A transpose, so that after the row operation we'll get to I. To the identity matrix. And now the row operations in the A transpose is the same as the column operations of A. So then that means after some after some column operations, we can also get to a some diagonal matrix. So after column operations, you can get to a diagonal. Alright, and now diagonal matrix basically means then the determinant of A will equal to some determinant of alpha multiplied by the determinant of I. And that will be just alpha multiplied by 1. And this alpha is usually like not 0. So that means this determinant of A cannot be 0. However, we already know that if we're assuming, if we're proof by contradiction, then this contradicts our assumption.
So this column operation is just like multiplied by a scalar or something to make it not like a one diagonal.
This column operation is like to do column replacement, to do column scaling, and linearity. That's like these.
Oh, on A or on A transpose?
On A.
Oh, okay.
Yeah. We do row operations on A transpose and column operations on A. We have a contradiction. Okay, and now we've proved the forward direction. So then in the future we can say if the determinant of A is 0, then A is not invertible, and if we know A is not invertible, then the determinant of A is 0. This also means if A is not A is invertible, if and only if determinant does not equal to 0. Okay. All right. All right. We have one more theorem for today. So if we have two square matrices A and B, the determinant of A multiplied by B equals the determinant of A multiplied by the determinant of B. So we can have a example. So let's say A is the 1, 2, 0, 4. Okay, we calculated this determinant to be 4, I guess. Is it? Yes. Okay. Right, because this is lower triangular, so we can just multiply it by these two. Okay. Now we have a matrix B. Let's make it upper triangular. So this is 5, 2. Let's just say it's diagonal. And we know the determinant of B is 10. Right, so let's calculate AB. A times B is, first entry is 5, second entry is 0, third entry is 10, fourth entry is 8. Okay. Then the determinant of AB is 40. Great. And that equals, if you multiply by these two, 4 times 10.